So what I want to talk about today is something that we have called the ISETBIoCSF generator, which is a software package that's in some ways you could think of as a wrapper around or a layer on top of ISETBIO, whose design purpose was to make it to provide tools that made it relatively easy to calculate using ISETBIO thresholds for stuff. So thresholds could be a contrast threshold, or it could be a vernier offset threshold, or it could be a size threshold in a tumbling E acuity task, or it could be a color threshold, whatever you're measuring the thresholds of. And our hope was to do this in a way that much of the machinery was sort of reusable, independent of what you were trying to calculate an ideal observer or computational observer threshold for, on the one hand, what stage of the visual system or what model of the visual system you wanted to use as the place you were going to evaluate the information by calculating thresholds, and what decision rule you decided you were going to implement in your calculations as a model of either an ideal observer or a human observer or something in between. So, and I think that as we thought about this, we kind of came to the conclusion that in any one of these calculations, there's a bunch of common things that you almost always do. And then there are basically three things that I would call are specific to a particular computational simulation or exercise that you might be involved with. And that's essentially defining the stimuli for which you're going to measure the threshold. So that's one thing. And in the CSF generator, the thing that does that, which I'll talk about a little more in some of the code details, is called we call a scene engine. So you have to have a scene engine because you can't study the threshold for something without deciding what it was you were going to study the threshold for. So scene engine is basically the stimulus specification. And then you need a model of whatever the transformation is going to be between scenes. And scenes can be, we typically think of them as like stimuli on monitors or on displays, but with they can include a temporal component. So they can vary, it can be a time varying stimulus. Then you need to decide, what's my model of the visual system that is going to define the signals whose information for performing a particular task you're going to evaluate. And we call that a neural response engine. We like the word engine around here. And so that basically is going to be the wrapper. That's going to be a wrapper around some ISETBIO code you need to provide, or you could use one of the ones we've kind of pre-provided, that takes scenes in and gives, actually in all cases, just a temporal sequence of vectors out. So in the end, we're going to think of any neural response as described by a vector, where the number of dimensions is the number of signals, like number of cones, number of ganglion cells, and the entries of those vectors are the size of the response to a scene. And by making the output just a vector, it sort of strips away all of the structure we might otherwise keep around. It means that the rest of the code just is completely agnostic as to what the neural engine is right now that you're studying, and in fact, to what the scenes are. It's just going to classify things. And so the last part that you have to sort of set up is a decision rule, like the ideal observer classifier, or a template classifier, or a linear classifier. And the idea of the ISETBIoCSF generator is we provided a structure to implement those three parts. And having implemented them, then you just don't have to do any more work other than sort of choosing number of simulated trials. And that. But basically, all the machinery that then runs that stuff, you just get because it's sort of part of the package or the package design. So what I kind of wanted to do today was take you through sort of how that goes, what the parts are, I'm not going to go super duper deep into the real details of the code, but I'm going to show you some tutorials that would kind of let you begin to trace down and show you some of the things that exist that you can already use, which actually I think are a number of the key parts of interest. So that's the idea of what I was going to chat about this morning, and I guess I hope I don't just be the only person who's talking for the next hour. So I'm just going to pause for a second and look at my window of view and say, everybody good with the plan? Any questions at this point? Okay, Fang, you don't really count as thumbs up since you've used the ISETBIO. You've written parts of it. But glad I haven't gone too far off track so far. All right, great. Let me close this again. So let's talk a little bit more detail about what this, I'm going to first, again, stay with this sort of high level view of these three parts, and then I'll switch to some code. I think that's going to be most helpful. But it's true that at this point, the issues of how the code looks might start to intrude. And if you're feeling confused, we can kind of reorder along the way. So what the scene engine has to do is it's a class implemented as scene engines are a class. So you instantiate the class of scene engine, and you have to provide it with basically a compute routine that you write that has takes certain arguments. It's got like the arguments it takes in, and the things it returns are defined. It's what's called an abstract method of the class. So you can't actually use the class until you give it a compute function that it then tucks away in. I mean, it's not quite, we didn't quite do it as an abstract method, but anyway, you have to give it a compute function that it then knows about as a scene engine, and it's going to call to do the real work of interfacing to ISETBIO. And the idea that, again, is sort of common across all of these threshold simulations is, in the end, you're measuring the threshold for some level of performance as a function of one stimulus variable. And that stimulus variable is what you're measuring the threshold for. And so we in the code and in the choice of the word CSF, we sort of call that contrast. But I put contrast in quotes because nothing about the code actually cares that it's contrast that's being represented. The key idea is the scene engine splits the description of scenes into two parts. One part, which it has to be able to keep regenerating different scenes, is it gets past the parameter, which is contrast is a good contrast. All we can say, it gets past contrast, and it has to generate a scene with that contrast. And when you initialize it, you have to say tell it everything else it needs to know, that your compute function needs to know to compute a scene. So if, for example, we were thinking about the contrast, the threshold for detecting little patches of gratings, intensity gratings, then the full specification is the field of view of the stimulus and the size of the grating and what its spatial frequency is, which the physicists use another word for, and what its temporal frequency is, and how it's oriented in the two dimensions, and if it's got color, what the color modulation parameters are. All that other stuff gets set when you basically instantiate the scene engine, and it tucks it away inside of itself. And then during the simulations, the scene engine will be invoked by the rest of the CSF generator machinery. And at that moment, that rest of that machinery will tell it the contrast it wants. And the scene engine's job is produce one of the scenes that you know how to make with the specified contrast. So that kind of encapsulates the stimulus part. And it says here on the bottom, the contrast parameter can really be anything. And we certainly have used this to do contrast thresholds. Thresholds is a color contrast. We've done size of tumbling ease. Meng-Shin has done offsets of vernier responses, and we've done some other things that we haven't published that I've forgotten about. So,
Here's you a minute,
yeah.
David.
Yeah,
I was just going to check whether everybody is familiar with some of this terminology. So,
good.
you use the word grating. Does everybody know what a grating is? Yeah, okay.
And that in the recent paper, that were great.
That's good.
That's why.
That's good. I just wanted to.
Yeah,
I think
sorry,
most of the other
that is a
things
little
are
jargony.
fairly, self-explanatory, but
I just have a question about this scene. So is it always just to simulate a screen, computer screen, or you can do it as a natural? Like,
Yeah, that's a great question. What I'll say is that we haven't. I don't think there's anything about the. I don't think there's anything about the CSF generator per se that, or the concept per se, that would require that it be on a display. But if you, but it is written so that at the moment, so that I would say the assumption that in the end, the stimulus can be described as existing on a flat pixelated display is pretty deeply embedded in the current code. So, and the key thing is that in the end, really, whatever the scene engine produces has to be understood by the neural response engines, and we've set up the neural response engines to take scenes in. And that's in some sense because ISETBIO, for the most part, is built around the notion that you start with a scene and you transform it to the retinal image. Now, having said that, really the retinal image is it might have been a better place to put the common currency if we had really been thinking generally, because if you were, for example, modeling threshold for detecting that an object in a 3D graphic simulated scene had been shifted in position and you wanted to render that in 3D using a graphics program, there's nothing that would prevent you from computing the retinal image from that more complex input. And the retinal image in vision is always there, so it probably would have been a better choice. However, I would say for anything in the short run, you've got to go through a flat panel display as part of your concept. It's also true that you could, anyway, maybe I'll just say that, but I don't think it would be that hard conceptually to generalize. We have published a paper and do have methods that use graphics rendering, starting with a 3D description of scenes, and they pass the ray tracing through model human eyes to compute the retinal image. That's very time consuming to run that code, and we don't run it all that often, but we have run it, and it is useful when you're thinking about 3D things or maybe more natural images.
David, could I just ask, so a while ago,
yeah, so I'm trying to find you. I'm trying to find your faces, which have vanished on my. I don't know why they've vanished. I can't. Oh, there. Maybe that's you. Nope, that's Spotify. Okay, well, I'll just keep talking. I sort of know what you look like.
Are we on a different Mac window?
I'm.
Like if you know the virtual windows.
Yeah, I don't know. It's okay. I'll find it sooner or later.
What I was going to ask is, a little while ago, I think you said that you had code to simulate a display, which is the raster scanned laser.
Sorry, yes. I should say that, yes, we can do that. And the reason we can do that is because you can describe the effect of an AOSLO with an equivalent stimulus on a flat display. So if that's what you were really getting at, Sarah, rather than the kind of complex thing I said, yes, we can do that. And we can do that because in the end, you basically can project out, had this flat display been here at this distance with these primaries, this refresh rate, it would be behaving like the AO display. And we don't typically, either for real displays or AO displays, get down to the level of the individual line rasters in our calculations. But again, I don't That's not fundamental, because you would just have to, you could model that as one line at a time in a temporal sequence whose frame rate was the line rate, instead of one frame at a time in a temporal sequence whose frame rate was the frame rate.
And so the scene engine does have a concept of extended time, so it does have a concept
Yes.
of frames.
It's definitely got the concept of frames, and in fact, the concept of frames sort of exists in ISETBIO in slightly, some places more than others, but basically, time in the CSF generator is a cell array of scenes, or maybe it's an array of scenes, and a variable that tells you the time base, and that gets passed around through things. So, for example, if your neural engine involved the eyes moving, it can have it can be the neural engine, the position, the actual model visual system can involve fixational drift, not surprisingly for this project, and how that's going can be specified independently of the time sequence, or I suppose even you could drive it with the time sequence of the scene. Okay. Let me. Oh, go ahead, Zara. Okay. It's possible I should be more. Let me just keep going with my plan, but it's possible that this will be, I'll say the same stuff again when we get to some code. So, a neural response engine. So we've got ISETBIO, which is typically what we use. Actually, I don't think there's nothing about the neural response engine that cares whether you instantiate your model using ISETBIO, but it's kind of what there's a certain amount of ISETBIO expectation in there. And so conceptually, it's defining the relationship between the scenes that come in and this vector of responses that goes out. That's its job. And so one possible neural response engine, and we have a certain number of, we have scene engines for Gabor patches in varying color directions, little Gaussian grading patches. We have scene engines for text and tumbling ease, and we have scene engines for Meng-Shin wrote for vernier stimuli as a function of offset. And there's a certain number of scene engines that you don't actually have to write because they already exist. We have scene engines that put things on AO displays, probably not your AO display, but the Berkeley one, and the Penn one. So neural response engines, we also have some of those. A particularly simple one, a relatively simple one, would be to look at the cone excitations of a model mosaic of cones, and that are limited by Poisson noise. So we have a scene engine that computes that, not surprisingly, since that's the sort of bread and butter calculation of ISETBIO. And when you set one of those up, you have to choose what the wavefront optics are going to be for your subject. We have some standard ones in there. You could customize it. You have to decide on the cone mosaic packing and the number of cone types. Again, we have kind of standard defaults for those, which pretty much are inherited here by things in ISETBIO. But in the end, the neural response engine is just giving this time sequence of vectors, and the rest of the CSF generator machinery is pretty agnostic about what the visual system model that it's using actually is. It just doesn't need to know. And as it says here, we don't tell it. And so you can use the same neural response engine with different scenes and with different decision rules.
Sorry, David, I had.
Yeah.
Was my question. Is the scene engine, is it closed loop? Can it have a closed loop control? So, for example, like, the stimulus, can its location change based on the eye movement?
Okay, that's a good question. How would we do that? So I think that we haven't thought about that. The way that you could do it, which would be I'll call it a hack, but it would work, is not to put that part in so I think not to put that. So if you had an eye position dependent stimulus, you probably would implement it by having the neural engine do some weird things that mimicked what it would do. That is to say, you could write the neural engine so that when it calculated the responses, if you had the neural engine incorporating stimulus dependencies, since the neural engine has the scene, it could do something like, okay, when I move my eyes to the right, shift the scene to the right to keep it in the same place on the retina before you pass it through ISETBIO. So you could write that code in the neural response engine, which would be a funny way to do it conceptually, because really what would be happening in the experiment would have the nature of the eye position would come out of, be tracked by the brain as a measurement. The experimenter would move the stimulus, and then it would produce the neural response. So conceptually, putting that module into the neural response engine between where it got the scene and where it computed the response is, if you were describing it to somebody, that's probably not how you'd want to describe it. But I think almost anything you would do experimentally of that nature could be captured by writing a little piece of a neural response engine that shifted the scene around. Now, if what was happening was more complex, so that, when you move to your eyes to the right, it turns red, and when you move to your eyes to the left, it turns green, I think we would have to write a more elaborated version of the machinery to do that, which really did have the feature that somehow you had scene engines could take signals back from neural response engines and do something and then pass it back in. And we are not conceptually, that's not set up. So I'd say you can do a limited amount of that. If what was going to happen to the stimulus is computable from the stimulus that you passed in, then you could write it. And if it's not computable, then you couldn't. Now, scenes can be complicated things. So even for more complex displays, maybe you could still do this hack, but it's beyond what we have really focused on in what I'll call this version of it.
So essentially, for philosophical reasons, you've decided to put the eye movement into the neural response part rather than into the scene part.
Yes. Well, so the reason the eye movements, the reason the eye movements are in the neural response is because, they are part of the neural response. And so that was a philosophical decision. Zara's pointing out that in a complex closed loop experiment, what the eyes do can drive decisions made by the experimenter, which can affect the stimulus. At least that's what I think that question was. And I would say philosophically, we never thought about that until right this second. So I'm sort of brainstorming about how you could model that kind of thing without having to go rewrite a fancier CSF-Generator, version 2. And you could get a certain way by overloading the concept of the neural engine with some of this stuff. But it would be, I think, philosophically weird, but might be just fine computationally.
Presumably computationally it's okay, sort of in the limit that the translation of the scene doesn't change any of the sort of optical translation of what that scene's like on the retina.
So if you wanted to model a stabilized experiment, probably what we'd do is just turn eye movements off in the scene engine and nothing would move and it would be stabilized. And that's sort of, I think, equivalent to having the scene and the eye move in complete perfect lockstep. But if you wanted to model, eye tracking that was imperfect, then you'd have to do, so there was a little lag between when the eye moved and when the stimulus followed, and you wanted to really track that down, you could, but you'd have to do it in this somewhat, I like Daniel's word, philosophically unpleasant manner. Okay, last piece, and then we'll look at some code. I'm getting better at finding this thing. Okay, is the response classifier engine. So, we have talked, and actually even, relatively recently in Mengxin's project about different decision rules. And so when you are simulating out psychophysical experiments, you need to have some method that takes essentially the neural responses on a trial, whatever the trial structure is, and it can have different things in different pieces of space, and it can have different things happening at different times. But in the end, in any, maybe not, in any trial-based experiment, there's a set of stimuli on a trial, then there's a subject response, and then more stuff might happen, usually the next trial. So you do need to decide what the trial structure is, and that involves passing in the stimuli that will happen on a trial to the neural response engine, which computes the vector of responses. And then the response classifier engine basically has to take those trial vectors and decide what was the response. And also, I think the way we have it coded, it may in the end, and Fangfang, you might remember, do we convert that to correct or incorrect on what the response classifier engine returns, or is that one level up in the code? Anyway, that's a detail that we'll find out when we look at the code. But so, for example, you might want to implement, and we often do, a kind of stimulus known exactly, ideal observer that has access to the mosaic of Poisson noisy cone excitations. And so, and we often want to model that for what's called a two alternative or two interval forced choice task. So if you are discriminating between a uniform field and a grading with some contrast, any particular contrast, what would happen in any trial is either a vector that was the concatenation of blank grading, or it was the concatenation of grading blank. Those are the two possible stimuli that could appear in this two alternative forced choice experiment, thought of as a single stimulus on each trial. And then the observer either says it was blank in the first interval or it was stimulus in the first interval. And that's either correct or it's not. And the response classifier engine, in order to do that as an ideal observer, needs to know that the mean responses, the mean excitations for those two stimulus possibilities. And when it's initialized, you pass to it whatever its model is. It could be this, that one, and that one you'd pass to it the mean responses when you initialized it to the two stimuli that can happen on each trial, and it would tuck them away. It knows it's doing the ideal observer calculation. So then on an actual trial later, in comes this noisy stimulus in that trial. It does the little ideal observer calculation, having access to the mean responses, and it kicks back its guess, and it's either correct or it's not. And that comes back to the to the CSF generator machinery, and you have just simulated a trial, and then the CSF generator machinery just repeats that over trials, whatever your experiment design is, and it computes up. And what it works to do for you is to define the contrast. So that's the response classifier engine, and then the wrapper, has code that will define the contrast on each trial, and it keeps track of the bookkeeping of what happened, and it fits the psychometric function, and it tells you the threshold. And so all that other work, you don't have to redo, at least if you like the way we did it, to run these things. So that's the third piece. And with that, I'm going to move these slides somewhere else because we're done with slides. And again, but let me pause. Okay. Yeah, okay, great. So let's open up MATLAB. Can you guys see my MATLAB window, and is it large enough?
So I realize that I do have a question. Sorry,
Okay.
So this is probably a silly question, but let me ask it anyway. quite often when we do two alternative force choice question type tasks, that's done experimentally because people are dishonest or biased or things like that.
Yeah,
ISETBIO is not. It's just
That's
a
right.
computer. So I'm just trying to work, what is actually the value in doing two alternative force choice?
you know, the
Yeah.
only real value is so first of all, you can do it however you want, but that is to say you don't have to model two alternative force choice within the CSF generator context. You could model either on each trial it's the stimulus or the blank, and the decision is which of those two things happened. And if, as you say, we can build the response classifier engine so that it doesn't cheat and is unbiased, and then we would get the performance of an unbiased, non-cheating, or not unbiased, non-lapsing observer. The only reason, and that would basically going to be it's up to a sort of a square root of 2 in performance, because you get you get more information on each trial in the two alternative force choice version. For ideal observer purposes, that would be just fine. And the reason, so really the reason we do it the way I described is a philosophical choice of I want the square root of 2 to be in there. So when I say the square root of 2, maybe everybody, I'm not sure everybody is with me on this. If everybody's with me, you can all assert it. But one way, so you have a blank that's noisy on every time you present it. You have a grading that's noisy, and they're not too different. As Daniel points out, one way to do the experiment is you present either the blank or the grading on a trial, and the observer's task is to say blank or grading. And in that kind of experiment with real human observers, there is a tendency sometimes for observers not to take a decision strategy which is biased, so that when the blank is there, they might respond stimulus more often than well, not a non-zero number of times, but more often than kind of an ideal percent correct maximizing system would do. And that's an interesting feature about observers. It has to do with the way observers make decisions. And when we study, we're interested in sort of the quality of the sensory representation as experimentalists. We really don't want how the observer is making decisions, and whether Daniel is biased to say yes and I'm biased to say no, which would produce differences in our performance, but might not be telling us anything about differences in the quality of our sensory information. We want to do the experiment in some way that minimizes bias or accounts for bias. And one approach, which is very time consuming, is actually to stay with the experiment that allows bias and run a block of trials where you tell the observer, we're going to pay you a penny for every time you say it's there when it is, and we're going to give you an electric shock every time you say it's there when it's not. Observers will get quite conservative if you do that, or vice versa. And you can actually systematically measure performance where you manipulate their criterion via rewards or punishments or prior probabilities or whatever. And then you can use that data to infer their decision bias and their sensitivity. And there was an industry of that went on as people were figuring these ideas out a long time ago. However, often we don't care about the observer's bias. We care about the sensitivity. So this other strategy where on every trial, let's say on the left is a blank or a grading, and on the right is the other, or it's the other way around, and the observer is saying left, right. Now an observer could be biased to say right on every trial, and that really is the same kind of bias showing up in this two alternative version of it, where both stimuli are presented every trial. But just as a matter of experience or as a matter of art, observers tend not to have left-right biases that are very large, or first interval, second interval biases that are very large. The biases kind of come in because people just hate I think typically they just hate saying it's never there. And so they start to say yes to blanks when the task gets hard. So as a practical matter, this two stimuli that both alternatives rolled together in every trial, and this trial structure being basically A, B, or B, A, reduces the bias in observers, and the field has kind of, I'd say to a large extent, decided, yeah, that's a pretty good paradigm. Let's stop worrying about observer bias as we do it, and let's get on with our lives and measure sensitivity. And so, okay, so that's all background. I hope that was helpful and not completely redundant with what people know. So in ISETBio, we could model it either way. And Daniel was pointing out that if we don't have any bias in the computational observer, we'd be passing fewer bits around and calculating faster if we were doing one thing per trial. But when you present both stimuli per trial, you're actually giving more information. You're driving twice as many pixels, and performance for an ideal observer gets a little better. And if you don't really want to think about how much better it gets and work through math, you could just stimulate it that way, and then you capture exactly what the experiment was.
And
Great.
also, if you're trying to measure actual performance, there's only the most efficient performance to test is the 2AFC test. So eventually there's a point at which you want to come out of ISETBio and say these results predict human performance, and then you'd want the 2AFC test.
Okay, thank you.
Yeah. Excuse me 1 second. I just got to blow my nose. All right. So let's look at some code. And I'm going to, so in the CSS, so let me actually, before I look at some code, let me just say something that's true and perhaps unfortunate. So we've been using ISETBio for quite some time. And just to maybe even to explain why. So before there was ISETBio, there was something called, there was ISETCAM. And ISETCAM was a digital camera simulator written by my colleague and collaborator, Brian Wandel, which he used to great effect actually as a consultant for Silicon Valley companies who built cameras and wanted to think about how the camera should be designed. And so it has in it the ability to create scenes and compute optical images, and then it's got lots of things about camera sensors. And when we started ISETBio, it actually was as a result of a conversation where he was describing this to me, and we sort of realized that, oh, this framework could be extended to capture and model human vision. So we took and made a copy of ISETCAM, partly because it was, anyway, he wasn't quite ready to release it freely because he was making money on it. Maybe that's why, I don't know. Anyway, we made a copy of ISETCAM, that was ISETBio, and we put in lots of things to model human vision, but we were basically using the ISETCAM scene description and some of the core code for optical images and core ancillary code. And as is the way of computer code, over time, changes were made and little fixes to ISETBio, and other changes and little fixes were made to ISETCAM, plotting routines, this, that. Certain conventions drifted apart, and it was driving Brian, who used both of these codes, completely bonkers, because he'd fix something in ISETCAM and then it would still be broken in ISETBio and vice versa. So we decided about maybe a year ago now that we were going to push these two pieces of software back together and have two repositories where the optics and scene stuff was in ISETCAM, which also would have the camera stuff, and the human biology stuff, for the most part, would be in ISETBio. And so we've done that. It's for the reason I just described. It's not 100% backwards compatible. And to date, I think everybody but me in my lab is still using the ISETBio master branch, which is the branch that's got everything in it. Fang's using that. That's the branch Mengxin has used. There is a branch of the ISETBiOCSFGenerator that pretty well tested on that. But we really need to move to this new version, or we'll just reproduce the problem that we went through all this work to solve, which is if you have two versions, they're just going to drift apart again. So this is a moment when I'm really encouraging people to take a deep breath and switch over to the new configuration, which is what I'm going to run here for you today. The other thing that went on is that Fang and I spent some time staring at the ISETBIoCSFGenerator together in the fall when she came to my lab, and decided it was time to kind of fix up some stuff that had gotten a little clunky. And in particular, there was a proliferation of routines to handle various special cases that really could be handled in a unified way. And so Fang spent quite a bit of effort writing a core common routine, and the special cases called through that. And then once we had that working, we started to just convert the code that makes the calls to call the common routine. That's also a little bit in progress. But I'm going to show you that version here. And this is all to say, particularly Zara, as you start, I posted in the Slack, use the dev, people good with branches, the idea that there are these multiple versions of code that exist on GitHub that you select by the branch. Use the ISETCAM dev branch, the ISETBIO dev branch, and the ISETCSFGenerator, I think it's called Technical Debt Payoff branch. Start with that, and you'll be in the forward-looking future direction, rather than in the direction where if something breaks, I'm just going to say, no, go use the new version where we fixed it. But it's also going to have a little bit of the feature from time to time, as over the next few months, you encounter something that is broken because it hasn't been updated, and it will be annoying. So that's just a kind of caveat about where we are today. I will say that much of what I've done in my software life this year has been to make sure all of the unit tests in ISETBIO, of which there were many, still give the same answers in the new version. And that took a shockingly long time to beat out a whole series. And sometimes it was bugs in ISETBIO. Actually, I should say, we made sure either they gave the same answer or we decided the answer they were giving was wrong and fixed it. But we did really, there's an extensive set of unit tests that now pass with the new version. And that testing framework exists in yet another repository, which if you ever want to see the tests, I'm happy to show them to you. Okay, so that's just a kind of general caveat. Yeah.
So I understand about branches. I had a question about how if you're using Toolbox to manage what you're using, how do you tell it what branches to use?
So the easiest way to tell it is just so I'll tell you what I do, which may or may not be compatible with. So I have this GitHub client, which I love and can't live without. I will show you. So it's called Tower, but anyway, it's my interface to GitHub. And I'm gonna, what did I fix here? Okay, I fixed a comment. I was working on doing some of this fixed comment to remove. So I'm making a commit comment. I've staged that thing. I just committed it. I just pushed it. And now here's my view of the ISETBIoCSFGenerator repository. And I'm working on the technical debt payoff branch because I've set that to be the head.
Yeah, okay.
And so the way that we work with Toolbox, and it's a little, and I have gotten myself confused about this, but the simplest way is I just make sure on the repositories that I'm using that I'm on the branch I want to be on my local copy. And then Toolbox just doesn't, if you don't do any heroic effort, doesn't do anything to your branches, and so you're just on the branches you want to be on. So that's how I do it. There's ISETCAM, I'm on that. I'm ignoring the master, the 92 commits to the master, which I'm never going to look at because I don't use it. You can also set up a Toolbox configuration file that will check out particular branches, but it makes another copy, and it's not, I would say it's not quite as slick as I like it to be. And I find it, now I've got two copies of the software on my computer. And when I edit, they're really separate versions of the repository, and it in different branches. And I find I just spaghetti myself when I try to do that. So I spaghetti myself less by manually checking out the branches I want. I get mad at MATLAB for not providing us with a package manager that was professionally done as opposed to the one that we had to write ourselves. But in any case, once I've done that, what I do is TBU's project. No, look at that. Okay, ISETBIoCSF. Oh, sorry, it's not TBU's project. It's TBU's because the ISETBIoCSFGenerator is a toolbox, and that therefore its configuration files are sitting on the web. And there's one that says -cam, and that it is important to use that one because otherwise it won't put the ISETcam part on your path.
Yeah.
And I think, you know, in 6 months we probably will just go get rid of the -cam and make the total default to do it this way. But there it is, updating everything. And having done that, I now am going to look at, and I guess I'll show you. So here we are. Here we are looking at. Oh, here we are looking at the ISETBIoCSFGenerator tree. And why there is a .NET file at the top level is mysterious and irritating, but there it is. It's some data. It says, oh, yeah, this is a hack, which is another caveat I should give you that mentioned this about that we have to fix soon. Okay, so there's a toolbox, and the toolbox has got in it. It defines. So I mentioned the scene engine. There's the definition of the scene engine class. There is the neural response engine. There's the definition of that class. There is the response classifier engine. There's the definition of that class. The quest threshold engine and the contrast threshold engines are things you pretty much don't have to touch, but I will tell you about it. And I believe that the response classifier engine, anyway, is this right, Fang? That's headed for deprecation land, right? Anyway, I
Sorry,
think
I was muted. Could you open that folder?
Anyway, let me just say, I don't think you need to know about this one. There's some stuff here we haven't cleaned out yet. But these are where the classes are defined. And then there are some really important, and I'll talk a little bit about these if we don't run out of time, helper functions that actually do all the kind of wrapping around these classes in order to do a simulation. So that's sort of where that stuff is. And then the other thing I think I mentioned, and this is the next, so those are the class definitions. Now, when I build a scene engine, there's this class, scene engine, and I told you I have to initialize it with a compute function that we call it a compute function that sort of builds whatever scene your version is. And so those compute functions live in their own directory. And there is a SCE for scene engine grading function. I'll show you how this goes in a little while. And another one, which is a uniform field temporal modulation, which is kind of an example thing. Actually, that's the first one, okay, which just creates a spatially uniform field and modulates its intensity over time as like a really simple example of a scene that you could study. And there's something for presenting that describes circular spots on some AO system, and something else that describes 2 spots on some AO system. That's because we were modeling experiments that we did here at Penn on detection of spots as a function of their size in an AO system. And so they're here as because we were using them, but also examples. And then there are some neural response engines. There's one, this one is I think the one we use the most, NRE, photopigment excitation, CMosaic. And again, I think we are in the process, we've kind of made this quite a bit more general, and these other versions with eye movements, without eye movements, single shot are sort of variants which are going to go away because we made one of them a little more general. Is that right, Fang Fang? That's kind of what I remember. Although we've already stuck
Yes.
some.
Yes. We already moved
We already
single
moved some. Oh, these are our retinal ganglion cell mosaic ones, which is we're just beginning to do. I'm not, but we do. So they're scene engines for the retinal ganglion cell model in ISETBIO and are a little more in flux. But Fang Fang is actively using them, and they're available to your modeling as well. And then there are some. Oops. Sorry. There are some pre-made response classifier engines. For example, response classifier engine Poisson is the ideal observer Poisson limited classifier. And the template distance is a classifier that says I got two templates for this, what the mean stimulus would be. Pick the one that's closer in a Euclidean distance sense. I think Meng Xin has explored that one. And that one happens to be written that it only knows about the two alternative forced choice task. Again, something which we might be able to squeeze out of it, but it's currently a little bit special case. So there are these things that are provided. And then I think the place where I would recommend that you start, just as an ISETBIO, is there's a directory filled with tutorials, and you'll notice that deprecated are the ones we're getting rid of because we thought they were handling special cases that we could handle more unified way. Needs updating are ones that are currently broken for some typically uninteresting reason, like they're using the wrong version to model the old version to model the cone mosaic that hasn't been updated. But there are some in here that actually work and that are useful. And the first one I want to talk about is the most basic one called T threshold engine. So this is a tutorial about the engines for computing an ideal observer threshold for something. And so here we are. And what I think I'm going to do, I'm going to vamp while I just run it. So you see what comes out. I think understanding what comes out could be vaguely helpful in understanding then what it does. And we have to wait for my computer to open its parallel pool. Is anybody else trying to use MATLAB on Apple Silicon Macs? It's very flaky, and the parallel pool just died. You walk away from your computer and you come back and your parallel pool has died and it has to start again. And they keep saying, oh, it's a bug in Java. You have to update Java, It's a little better, but it's still broken. So we're going to wait. Any questions on what I just said? Well, I think this will now run pretty fast because I ran it yesterday. All right, so it's chugging through. It's telling you something about what it's doing, which is whatever it's doing. Now it's thinking in some way. It worked yesterday. I hope it hasn't crashed. That would be very embarrassing. Oh, it's chugging away a little more. And it's basically telling you something about what contrast it's presenting for whatever the stimulus is, which I haven't told you yet. But something's thinking, it's estimating something, it's building some. This one might be actually using a learned classifier, so maybe building. I think it's building classifiers, and we'll kind of go through that. But you see, it's telling you, all right, whatever this was, I ran a very low contrast. I got 27% correct. No, 97% correct, 96% correct, 48. So it's choosing different contrasts, which actually give different percent correct. So it's kind of mapping out according to its own internal logic what contrast it wants to show in order to map out a psychometric function, which it is trying to do. So this is 50% correct, down to low. Should have chosen an example that ran faster. optimistic that it's going to finish soon and that it's worth sitting here for a few minutes.
So David, the best place to look for tutorial is ISETCSFGenerator, not ISETBio.
For
Is that
this,
right?
for what I'm talking about now today, the tutorials that explain the ISETBiOCSFGenerator are in the ISETBiOCSFGenerator repository. And yes, so that's where this tutorial is. And the other one that I'll show you. By the way, you guys can tell me when I've gone on too long. I don't know what your complete agenda is for the morning.
We're
Guess you're all
flexible,
there. You're all
David.
there for the day, and we're going away at
Yeah.
10. Okay, I thought this ran faster. I ran this yesterday.
Probably when you've got Zoom running.
Yeah. Let me just, okay, so rather than sit here and use up everybody's time without having anything, watching the grass grow, let me work through, my goal now is to just kind of talk through how this tutorial is structured and to give you a sense of how these pieces I've described more abstractly. It's really chunking away now. That's good. All right, so this is going to compute a threshold, a contrast, basically a threshold for something. And I think the particular something is just a uniform field. So the first thing this code has to do is to instantiate a scene engine, which probably at the time we had a different name and change. So I'm going to update this comment. So this is set up with a little switch statement. So then, there we go. Okay, so good. So this thing is, this program is going to have a spatially uniform field. It's going to compute the cone excitations, and it's going to, I think in this case, it's going to learn a linear classifier at each contrast that separates a uniform field with no modulation from one of the different contrasts. And then it spent some time choosing different contrasts to show and mapped out as a function of contrast the percent correct, and it fit a psychometric function to it, and it printed out to us that the threshold was minus 2.55 log units of contrast for this particular case. So, and what you see in this plot is that the size of the circle is the number of trials it ran at the particular contrast. So it's using an adaptive method that tries to put the trials in the place that actually tells you about threshold, which is clearly in this region. And so sometimes, you know, it did a trial up there, and they were 100% correct. That's not very informative. It did a trial here, enough trials there to figure out that was 50% correct. It maybe just did a very small number. No, that's just no, those are trials. It did some trial down here that was probably a very small number of trials, and by chance it was never right. But it put most of the trials in this portion of the psychometric function where it's telling you a lot about how the shape, how it rises from 50% to 100%. And this is a Weibull psychometric function, which in our earlier reading is the same thing as a quick psychometric function. It was the thing that was used in that probability summation paper. And I believe we tell it, we want to know both about where it rises and also about how steeply it rises, the so-called slope. So it needs to put trials along the steep branch, and this method called Quest is what chooses those trial levels for us in the simulations. You can set it so you can just tell it, I want to run this set of trial levels, but here it's trying to be clever. So that's what it did. And really, that calculation is the core of any study where you're measuring computational thresholds, because in went some scenes with a parameter, and out comes for one particular choice of scene conditions, out comes the simulated psychometric function through some model of the visual system with some decision rule, each of which is specified as part of the simulation. So that's what this tutorial shows you how we do. And I think in some sense, once you understand that, everything else is details, which are non-trivial, but are there. So here we go. And that's, again, there were questions. I can't see, again, I've lost you guys. I don't see you. Well,
We're
okay,
still here.
so
It's all right.
you're still there. Great. Oh yeah, there you are. It's funny. Now you're back. Everybody looks alive. Excellent. So this code was structured with the possibility that we might someday illustrate some other scene engine. But in fact, the only case that the tutorial set up to handle is this uniform field case. So this is a simple example thing, probably not something you would really spend much time studying. And so we're going to instantiate, so we're going to instantiate a scene engine. We're going to, when we instantiate it, we have to tell it the compute function that we wrote. Well, you know, it's there. We wrote it, that knows about how to build ISETBIO scenes that describe a spatially uniform field, and that knows how to take contrast, and that means, you know, give me more or less intensity according to positive or negative contrast. And when you instantiate it, you have to pass a parameter structure. And that parameter structure is something that needs to be understood by your compute function. So the scene engine doesn't know about what these parameters mean. It just stores them. Your compute function has to be able to build scenes having been handed a contrast. And since there's other stuff it needs to know about within the domain of uniform fields, it has to get some parameters. And so in the SCE uniform field temporal modulation compute function, this guy, we wrote it so that it takes a parameter structure, and we modify some, we set up something here. Okay, this is going to be a 1 second presentation. Stim onset. The thing is going to turn on in frame 1, and it's going to last for 1/10 of a second. So we gave it those parameters, and you might be wondering, well, is that all it really needed to know? I mean, didn't it need to know how big it was, and what color it was, and how fast it was being sampled over its 1/10 of a second duration? And the answer is yes, it did. It does need to know that stuff. And there are 2 ways it might know. One of which is we might have hard-coded it into the example function, which just would make it a little less flexible. And the other is, these aren't necessarily the only parameters of this structure, because you can see we initialized it here. SCE params, this is our compute function. And you say, well, why are they calling this compute function with no arguments? Because I told you it had to take contrast. And the reason is, by convention, the way we have built this stuff is that compute functions, when called with no arguments, return a structure with default values for all the parameters that they need to be passed. So if I were just to execute this, not giving it any arguments, you can see that the full set of parameters is the field of view in degrees, the mean luminance, the frame duration, the number of frames, the frames in which the thing will be turned on, and the number of pixels that span the visual field. And that however we wrote this, everything else that you might need to know to build a uniform field, we baked in as hard code. It isn't flexible, but these parameters are understood by this function and modify how it does it. And what we've done here is gotten the default parameters and said, well, no, we don't want a 50 millisecond thing. We want a one frame. We don't want 4 frames. We want 1 frame, and we want that frame to be on, and we want that frame to lance a test. So we made a slightly simpler stimulus here than the default parameters would produce, because the default parameters would produce a 4-frame sequence and it would only turn the stimulus on the middle 2 frames. And but we've left the size and the luminance alone because we didn't muck with them here. So anytime there's a compute function, you wonder what its parameters are. And this is true for the compute functions for the neurorespond engine and the response classifier engines. The compute functions always have to return their own default structure if you call them without an argument. If we open this thing up, we find that it says that if called directly with no arguments, it does not compute anything and returns a struct with the default parameters that define the scene. If it's called with arguments, and that's what happens when it's called from the scene object, it computes a cell array of scenes defining the frames of a stimulus and the temporal support of the frame. So it returns to you data out, and this helpfully tells you that data out is a structure and that the scene sequence is one of its fields, and a vector of what time those frames happened is the other. So that's what this thing returns. When it's called by the scene engine, it takes in the scene engine object, and that's because the scene engine object has actually tucked away the parameters. I don't know. Sometimes the scene engine object has information that the compute function might want to use. Not always, but the scene engine object can. And but mainly what this thing needs to take is, what contrast do you want my scene at today? And what are the parameters I should compute it with respect for, which of course it knows about because it's written to know those parameters. And the scene engine, when it calls it in this form. So that, and then this thing has got some examples that might actually run. I don't, oh, there's a method. Okay, interestingly, let's just do this. So there are the default parameters. I showed you that already. I instantiate one. Here's how I could generate a scene. I'm directly calling the scene engine object here with test contrast, and it will in turn call this thing. Normally we don't use the scene engine object directly, but this illustrates sort of what you can. So this thing is going to produce now sorry, Ken, if you see down here, it's going to produce a cell array, 1, 2, 3, 4 frames, because those are the defaults. And if I do the test scene sequence sub 1, I better find an ISETBIO scene, which we will recognize because that's what they look like. And there's 4 of them. And then it also tells me that I should think of those as being happening at these times every, in this case, 50 milliseconds. So, and then there is this one other thing shown in this example, which is that the scene engine object apparently has a method whose purpose is to show you the scene sequences that it knows how to generate. And so this is part of the scene object, and we can do that. And it says, there's what frame 4 looks like. I don't know why it's purple, but apparently that's how we set it up. And here is how the gun modulation for R, G, and B happened over time for this particular scene sequence. So somehow the visualized thing figured out that this was, or decided, or is coded to have a reasonable way of looking at what was in your scene sequence.
Sorry, so it doesn't show the time changing stimulus, it just shows a frame of the stimulus?
Well, it shows you this particular view appears to show you one frame, the last frame, and then it shows you the time varying gun coordinates. And I actually honestly don't remember in general what other kinds of scenes quite what's shown by this method. It may be, but it does something. And in general, there's often a little challenge we have, which is, this is an example of, there are these remembering quite how all the visualized things work and what the options are. And unfortunately, you just kind of have to at some point, go open the code and look. But there are often visualized methods floating around that can be helpful for debugging. Okay, so that's kind of, and I'm not going to go. So I would say that let me just say, the basic conceptual structure of the other engines is like this. I'm not going to go down into those bits of code here. I'm going to kind of stay at how did this thing work. So we built this scene engine, right? So now we've said, today we're studying thresholds for a uniform field getting a little brighter. How much contrast relative to whatever zero contrast was defined as do I need to have? So I need to decide on my neural response engine. And so we're gonna study here one that computes photopigment excitations of a cone mosaic. And it's gonna use that compute function. This case, we have another one that you can look at. The simplest neural response engine we could think of is one that doesn't even involve exactly the nervous system. You just say, well, the physicists tell us that photons are discrete. They come with photon noise. At every pixel of this image, we're just going to view the neural response as the image, but we're going to make it noisy by adding photon noise. So sometimes people actually are interested in calculating with respect to that, because that is the upper physical. If you say, how well could an ideal observer do limited only by photon noise in the stimulus with exact access to all of the pixels, nothing could do any better than that at the task, right? That's limited by the physical variability of photon uncertainty. And so that scene engine, NRE scene photon noise, implements that. And sometimes people like to ask, how well is the visual system doing relative to that benchmark? We haven't done it much, but it's here as an example. So you could change this string to that string and it would do this other thing. But let's just look at this one. So we define the compute engine, and just like with the scene engine, if we just do this, it gives us the defaults are the optical image and the cone mosaic, and those are ISETBIO things that have parameters. So if we did, we can go take a look here, neural params.optics params. It's going to do the optics from a database of subjects who were measured by Polans that we have. It's going to pick subject 10, and it's going to use a 3mm pupil. That's the optics that are instantiated by default. And then the cone mosaic params are things that define the cone mosaic. Well, how big is it? Where is it located in the visual field? So this is foveal, 0.3 degrees squared. The integration time of cones is going to be 100 milliseconds. And the field of view, I'm not sure what the field of view and the size. This is confusing to me. Somehow, oh, the field of view, I don't know why those two numbers don't seem like they should both exist, and not quite sure why they both exist. That's probably that's fine. Do you remember how the size differs from the field of view here?
I think what we use is size degrees, and the fovea did. I normally don't change it. Yeah.
So this is what I would call what you get with software that you wrote yourselves. Sometimes there's something screwy. I will make a note that so something confusing about this. Now it's possible we could run the experiment of going and asking, did we explain this in the comment for this thing? This is the same kind of stuff. All right, I'm not going to try to figure that out on the fly, why there are two separate fields that seem to be specifying the same thing. But I will try to, that seems like an unfortunate bit of design. All right, but here we go. So we set up the where are we here?
So is it
Oh, sorry,
possible?
it's the wrong, I'm in the wrong, I'm in the wrong. Sorry?
I was thinking maybe it's because one of them, when you don't have a square, like build up
Yeah,
view, you to have different.
that's possible. I think we should just say, this is confusing, I should fix it. We, anyway, but you get the idea that you set up the parameters for your mosaic. Maybe they're a little overspecified. Now there's some other stuff that you do have to tune up when you do this simulation, which is, it's going to try to find contrasts that characterize the psychometric function, and it really is helpful to have if you give it some guidance of a reasonable range. And so these parameters here have to do with, I would call it an uninteresting but important part of these simulations, which is going to simulate out contrast. You've got to tell it, okay, what range of log thresholds do you expect might be happening? How finely do you want to allow it to sample in discrete levels, that range? And similarly for the slope parameter of the Weibull psychometric function. And it just turns out, and it's a little confusing, these numbers are negative. It's the negative of the log of the threshold that we specify. And that was probably a bad decision to make it the negative, because it's a little confusing. And I'm going to add a comment here. The threshold values are specified as the negative log 10 threshold for reasons beyond knowing. Okay, so we set that up. Now we have to build the response classifier engine. And here are three possibilities that we have pre-computed. This is the Poisson ideal observer. This is one that was, and part of why this took so long to run, where it actually takes a big set of samples of noisy instances and learns a linear classifier to do the task, and then applies that linear classifier. And so when we were chugging through this program, and it would sort of do some stuff, and then it stopped for a while. Those stops were happening when it was getting a contrast it hadn't seen before and had to go fit the support vector machine linear classifier before it could simulate trials. But I think it's illustrative to show this version. If you switch this to the Poisson, it will do the Poisson ideal observer, and there it doesn't really have to learn very much. It just needs the means. And if you switch this to the template distance, it's the template distance one, which again is faster. So
David,
you now, yeah.
It might possibly help just to elaborate.
Okay, I didn't actually.
Easy conversations on this, and I remember.
I can't quite hear you. You're a little muffled, Daniel. Daniel, you're a little muffled. I couldn't actually understand the words.
Okay, just if you could say quickly a little bit more about each of these classifiers, just to remind us.
Okay,
exactly
sure.
what they do.
So let's start, and I think the one we've often talked about is the ideal observer. The ideal observer, stimulus known exactly, and it's for the Poisson noise. You tell it the mean response to each stimulus when you set it up, and then having told it that, it computes the likelihood with respect to the Poisson noise, which is defined by the mean of the two alternatives, and picks the alternative given a noisy instance that's more likely. And that is given the particular noise of the stimuli and that it is Poisson distributed, that is the percent correct maximizing algorithm. You can't do better than that. It does assume that the visual system knows a lot about the experiment. The template distance classifier also gets the mean response to the two alternatives, But rather than doing the Poisson limited ideal observer calculation, it computes the Euclidean distance in the response vector space to each of the templates, and it picks the one that was closest. That is actually the ideal observer rule if the responses are limited by Gaussian noise and the variance of the noise is the same along every dimension and the same for all alternatives. Then that is an ideal observer, but it's not the ideal observer more generally in Gaussian noise if there's correlations or different variances. And then the PCA SVM classifier is one that is given, in order to train it, it's given a big pile of noisy samples for each alternative. So it doesn't get told by an oracle what the responses to the two stimuli were in the noise-free case. It gets told a pile of examples, and given examples from class 1 and class 2, it fits a linear classifier that best distinguishes those classes after having applied a principal components analysis to reduce the dimensionality. And it uses something called a linear support vector machine to do that fitting. And that's a kind of interesting choice because it, first of all, it degrades performance relative to the ideal observer, and it puts back in a little bit of a model, not completely realistic, of the fact that the observer probably doesn't get told by an oracle what the mean response is to all the stimuli. You can, by the way, initialize the ideal observer by giving it a pile and have it take the mean of those. But so those are three different, what I'll call, models of how the observer makes the decision. And they're all illustrated here because they're sort of all cases one might want to use, and kind of, I think, useful cases to benchmark things and think about. And so we will look at how this one works.
David,
and in
can I just
particular, yeah.
Sorry. Just checking, I haven't misunderstood. You were saying that in the first two cases, it knows the mean response associated with both stimuli.
Yeah.
Essentially, that's the noise-free response.
The mean is the noise-free response. That's right.
You were using those terms the same.
I'm sorry, I'm using, those are in fact, at least for Poisson noise and Gaussian noise, synonymous.
But it's not true for all types of noise.
It's true.
If they're not...
I think you could produce a noise distribution where the mean response has the feature that in some sense no noise has been added. And so are there cases where the mean response, I don't know, you could come up with some other thing you would tell it that wasn't the mean that might be more useful under certain noise distributions. But really the key point is that we're going to pass it, as you'll see below here, some initialization information, which is specific to the particular classifier that we built, because it has to be the kind it expects. And again, you can write your classifier engine to take whatever initialization information it wants and to use it however it wants. But for these cases, that's what it does.
Thank you.
I'm going to skip over. So this stuff here, I just, particularly looking at the time, don't want to. This is stuff which you probably sets up the algorithm that chooses the trials, and it has a method of constant stimuli version and an adaptive mode version, which is what I showed you, and yet some other version called a validation mode. Maybe it does a method of constant stimuli in a slightly different way. And that's important, but I think we just can't do everything here today. So I'm not going to delve into the details of that. And now what we're going to do, okay, so now the action begins. We're going to say, well, look, this experiment has got a uniform field. Well, that's my stimulus with zero contrast. So I'm going to build once, because I'm going to reuse it a lot of times. I'm going to have the scene engine tell me, here is the null scene sequence and its temporal support. So this is the blank in this task that we're modeling. And now I'm going to go in a big loop and run a lot of trials for different test contrasts. So was somebody trying to say something? I heard a noise.
No, I think it was a table squeaking.
Table squeaking. Excellent. The table's unhappy, but we don't have to worry. So this is sort of the action here, the whole thing, and it's not that long. I can't quite get it. I can come awfully close to getting the whole thing on my screen at once, but not quite. So the estimator is this Quest thing that I said we were going to ignore, and it's somewhere this got set up. Estimator got set up. Estimator is a class that tells me when I ask, I go estimator.next stimulus, and it says, here's the log contrast I want you to run next. That's its job, and we'll see how we update it so it keeps doing something smart. So now I got an initial contrast, and I'm gonna loop, and also it tells me, I think you're done now, which either can be because you ran all the trials we set it up to run, or because it thinks it's run long enough that it's brought the variance of the estimate down to some criterion. Whatever rule you set it up with, its job is not only to tell you the next contrast, but do you have to keep going? And we say, okay, there's the contrast. So next flag is true, run some more. We haven't yet tested any contrasts. So we're gonna compute the contrast we want by taking 10 to the log contrast, great. We are going to ask ourselves, and this is important, have we run this contrast before? Because building the classifier takes a while, and what you'll see is when we build it, we're gonna store it for that contrast and not build it again if it ever comes around and asks us to do that one again. So, okay, the first time we surely haven't run it before because this was empty, so we haven't done it. So we better say that we're about to run it. We're going to add this contrast that we're running to a list. We're going to find where in our list of contrasts this one is. We are going to compute. Now we're computing we got the blank. Now we're computing the target stimulus for the contrast that we're about to test using our scene engine. We know that because we built it this way, that the temporal support is the same. If we're different here and here, we have a big problem that would crash, and that would be a bug. And we're going to train the classifier. And so this is now important. We're going to train the classifier using a routine that is a core support routine called compute performance, whose takes in, and so this thing, compute performance is sort of your friend in the sense that, and I'm not sure we're going to get to unpack it fully today. This is going, I think it's probably good that we're going at this pace. But compute performance, let's just look at what it takes. It takes a sequence of, it takes the null scene sequence, that's the temporal sequences, the blanks. It takes the test scene sequences, which for this index, so that's the test scene sequence at this contrast. It takes the temporal support. Now, ntrain and ntest are the number of trials that we said way up here. We said when we train, pass it 512 trials, examples of the stimuli, and make them noisy, because we said they should be noisy by putting random here. And when we test, we're going to test just batches of 120 trials, it turns out. If we had used the Poisson, we would have said, you don't need to do any training. You don't need any noise in the training. We're going to give it the noise-free thing, and it only needs one instance because it just needs the mean. But when we test, we're going to test a batch of 120 noisy trials. And it turns out there's a lot of overhead to certain things. So when you're simulating, you wouldn't do this in a real experiment. You might as well, while you're down there simulating for a contrast, do a bunch of trials, because that typically goes relatively fast relative to the training. And so you get a more accurate estimate of percent correct. But if you really want to do it one trial at a time, you would set that to 1. Okay, so here's compute performance. And so we tell it that. We give it the neural engine, and we also tell it how many trials do you want to test on. We give it the test flag. That's whether those are noisy. It would be kind of odd to test it on noise-free data, but if you wanted to make sure that nothing was crazy, I guess you could. You give it the neural engine. You give it the raw classifier engine, which is the untrained. That's a classifier engine that hasn't been trained. And we're going to use it. And then you say, don't save save the responses. I think stores them inside somewhere. We don't want to do that. Don't do any visualization. And there's a special case, because we do it so often, for two alternative forced choice, which is set here to be true, which basically says the compute performance is going to do this stacking that I described, rather than treating these as one interval stimuli. And back from this compute performance, it's going to generate the training examples. It's going to do the PCA. It's going to train the support vector machine, and it's going to be able to do that because the classifier engine knows how to train itself. That's part of its job, and it's going to call it saying, train yourself, and here are your examples. The classifier engine will then store inside of itself, because it knows all it needs to know about the support vector machine and the PCA. So it will have that stuff. And this version of the classifier engine is the one that's got all the trained information for this contrast. And this is predictions as a vector, which is basically for each simulated trial, was it correct or incorrect? So compute performance is actually kind of important. Maybe we'll have a chance to look at it today. Maybe we'll pick that up. Maybe you guys, I think actually given that it's 5 of 10, 10 of 10, you guys will know that that's a place to go look and see how this stuff gets unpacked. But the rest of what happens here, we could get through the rest of this routine. We now use a copy method on the classifier engine because MATLAB is a pass-by reference on objects. So we want to pull out the trained version of this thing and not have it be clobbered by the next one we do. So you actually have to copy it. Pass by reference and pass by value, is that something that, anyway, if we just didn't do this copy, we'd have a pointer to the object, and the next time we did something with it, it would overwrite what we just did here. So we copy and save this trained classifier. If the next time we come by, we do the same contrast, we've got the trained classifier, now we would pass it to compute performance, and we would say, nope, don't train by putting this black empty matrix here, just test, because we've already trained it, and it will just give us the predictions. So this bit of code, this bit of code is simulating the trials. Yeah.
Sorry, I have a question. I don't know if I've got confused or not. So this classifier, I mean, this computation is just classify based on the scene, not the output of mosaic, not
no, it's doing it based on the mosaic responses, because it's got the neural engine.
Okay.
And its job, so we pass it the scene, because that's sort of the part outside the visual system, and then it computes the neural responses for you. If we had a different neural engine, nothing in this code would change. We'd just pass it a different neural engine. It would compute different responses. If we wanted to use a different classifier, nothing in this code would change. We'd just pass it the different classifier engine. If we wanted to do it for a different stimulus and a different variable, nothing would change. We'd just pass it. We just use a different scene engine up here. So in some sense, right here is where we're seeing the design feature of this code, which is really what I wanted to convey, that you provide these three parts. And this part I'm showing you here, other than tweaking some numbers and a few things that are specific, this part basically doesn't change at all. If you're simulating vernier thresholds, you're simulating contrast thresholds, they're eye movements, they're not eye movements, none of this changes. It's all the work is in specifying those three parts of the model, plus a little bit of thought to your quest engine. We watched those printouts come by. I tested this contrast. This was the percent correct. And this thing, then the other key thing is, at some moment we say, please, and there's a particular, it's a little bit call into this estimator. we're doing, we're updating the estimator. We're telling it what happened, and we're telling it that this is Quest trials and they're blocked. And in this other way, we're just telling it there were multiple trials. This is a little clunky. Maybe I should try to get a wrapper around it. It turns out, for efficiency reasons, the way you want to update your estimator method depends on whether you block the trials into big chunks or not, but it's not terribly interesting. All we're really doing here is saying, what contrast did we run and what happened? And we tell that to the estimator, and then we come down here and we say estimate. And then I think, where do we get the next? Okay, so where does next flag? Oh, next flag. This when I do this, it tells me the next contrast it wants me to do and whether I should actually do it. And so I just now loop here until this estimator thing tells me I've done enough. And then I make a plot of the results, having told it to actually calculate threshold using maximum likelihood methods from all the data. And it makes that little plot we saw at the end. And there's some option here where it could run a method of constant stimuli, which I won't show you. So that is that's the core of the thing. I'm going to save this because I fixed a comment. I think you should go through this and take a look, particularly at what happens in compute threshold. And we can pick another time, one of our regular meetings, to unpack that a little bit. This tutorial here, which I'll set going, it probably will finish. This actually runs out a full spatial contrast sensitivity function for the Poisson limited ideal observer. And here it is generating a very low, you can see a very low frequency grading at threshold, and it's psychometric function. And it's chugging along. It's going a lot faster because the Poisson ideal observer calculates a lot faster than training support vector machines. And so this is now, in this tutorial, there's a little extra loop that loops over different spatial frequencies and shows me this ran 4, 8, 16, and 32 cycles per degree. These gradings, these psychometric functions, and here is contrast sensitivity as a function of those things. So that example is a little more elaborated, also, because it's now studying threshold as a function of something else, but it's just really a loop around what I showed you. And then I think the other piece that's useful to know, and then I will really stop, is that rather than, there's another function which is very helpful called compute. We looked at compute performance before, and it was in a loop. Compute threshold is that loop wrapped around compute performance. The loop that was in T threshold engine is encapsulated into this other function, compute threshold, because you do that so often. And really, once you kind of have a feel for what that's doing, you don't want to look at it again. So really, this thing goes all the way from these pieces to the threshold. All right, I'm going to stop.